Hi everyone, my name is Hoa Nguyen. Today I will present our work entitled Computational Efficient Methods for Estimating Unknown Input Forces on Structural Systems. This is a joint work between the University of Adelaide and the Australian Department of Defence Science and Technology. Our work focuses on the problem of estimating unknown input forces on a structural system, which is an important task for condition monitoring. Condition monitoring is often used in fault detection or predictive maintenance for structural systems, which helps to optimize the operating and maintenance costs. It can be shown in the left figure about the life cycle of a machine. Condition monitoring helps to improve maintenance costs that extends the lifespan of machines by only replacing faulty components right before they fail instead of replacing components using traditional schedule-based methods. State estimation of a system plays an important role in condition monitoring the structural health of a civil or marine engineering applications. For instance, it can help to predict fatigue damage in a structural body of a tower or to reduce vibration transmission in marine vessels by developing a hydraulic dynamic observer. One of the popular methods in state estimation is to model systems directly in entanglement, so-called state space modeling, by describing the relationship between state variables and measurement square-based rules. Popular base filters include Kalman filter, extended Kalman filter, and extended Kalman filter, or particle filter. Their applications are based on the linearity of the model. A structural system can be described by an NDOF mass spring damper system as shown in Figure 1. Here, we assume that we can have sensors mounted on each mass, and the unknown input force F is applied on mass number 1. The DOF is comprised of the displacements and velocities that characterize the displacements of the masses related to its initial location. Early efforts of estimating unknown structural states using measurements of displacements or velocity has been investigated. However, it is extremely challenging to measure the system displacements and velocities directly in order to apply a standard Kalman filter when its state and measurements variables are only displacements and velocities. In practice, commonly available measurements data of a structural system are only acceleration data collected using accelerometers. There are three aspects of structural monitoring. First, estimating the structural states only. Second, estimating the structural state and input force. Third, estimating the structural states, the input force, and system parameters together. We focus on the second problem by assuming that the system parameters are known. The NDOF structural mass spring damper system can be described using equation 1 in a metric form. A considered problem is to estimate the unknown input force Ft using only accelerometers, the same components on smartphone devices. We consider two approaches for estimating. First, unknown input harmonic force, for example, a sinusoidal form, and second, estimating unknown input force without any priors. Let's review some related work of our considered problem of estimating the input forces and its states, which can be categorized into two sub-problems. First, without direct fit-through to measurement, which requires the unknown input force to be differentiable. For example, a sinusoidal force. Here, the MVU filter can be used since it's an unbiased and optimal filter. Second, with direct fit-through to measurement, which means that the input force is unmodeled and without any priors. There are three state-of-the-art filters for this problem: GDF, IKF, and DKF. Although these filters can estimate the unknown input force accurately, its computational demand is rapidly high, which prevents its real-time implementation for large and complex NDOF structural systems. First, let us consider the problem of estimating an unknown input harmonic force. For example, a sinusoidal force is shown in the right figure. Assume that the sinusoidal force applied to the mass number 1 has the form in equation 2. By taking its derivative, it follows the form in equation 3. By incorporating the acceleration as one of the elements of the state vector, we can characterize the continuous system in equation 1 into its state space model, which presents the dynamic evolution of the vector state at time k-1 in right-hand side to time k in the left-hand side. Under the assumption that the dynamic and measurement systems are disturbed by white noise, we can have the following state equation without direct fit-through of the k-1 into measurements yk given by equation 4 and 5. Since the k-1 only appears in the dynamic equation but not in the measurement equation, we call it the without direct fit-through system. The solution, since rank of Hg equals rank G equals 1, we can apply the ambiguous filter, an optimal filter, to estimate the unknown input force. The ambiguous had a similar form as a Kalman filter for its states, mean and covariance prediction step. For unknown input estimation, after a few algebraic steps, we can estimate the k-1 using equation 9. After that, we can use a fast Fourier transform algorithm to extract the unknown augmented f0, omega naught, and frequency omega naught of the k-1. However, if omega naught is correctly estimated, the estimation error of input amplitude f0 compared to its ground truth can be substantially large. The ambiguous had a similar form. Now, we move to the second problem of estimating unknown force without any priors. In this work, we formulate the problem as a linear system with direct fit-through of inputs as a to measurement. Since the input force is unknown, we cannot take its derivative to apply the discretization method that includes the acceleration as an element of a state. Instead, by selecting the state vector comprising of its position and velocity, we can have the state dynamic transition equation in 10 and the measurement equation in 11 when only acceleration are measured. Assuming, as before, that the dynamic and measurement system are disturbed by white noise, we can have the following state space equation in 12 and 13. Here, Qk and Rk are zero mean Gaussian process and measurement noise. Note that we have the term Fk in both dynamic and measurement models. Third, this system is called a linear system with direct fit-through to measurements. In this work, we define the ensemble Kalman filter based on AKF filter by combining the ensemble sampling method from the ENKF filter and the AKF filter that augments the unknown force into state in equation 14 and the resulting augmented state equation in 15 and 16. Here, QAK is the augmented white noise. Suppose that at time k, the augmented state HAK is approximately by an ensemble of Q possible states in equation 17. Then the ENAKF filter can be described using the two following stages. State 1 is called the forecast stage by propagating the ensemble states to next time and calculating the ensemble measurement based on the predicted ensemble states and measurement model. After that, the covariance error Pxy and Pyy can be calculated using equation 18 and 19. The stage 2 is called analysis stage, where the Kalman gain is calculated using equation 20 and the predicted ensemble state are updated. Note that the Kalman gain in 20 is calculated via 18 and 19 instead of the full covariance matrix of Pii with much higher dimensions. Therefore, the ENAKF filter leads to substantially reduce the computational cost. We present the first experiment for the problem of estimating an unknown harmonic force using without direct fit-through formulation. We estimate the force parameters using a minimum variance unbiased filter and a fast Fourier transform for a 100 DOF system. An external force with amplitude f0 equals 250,000 Newton, angular frequency omega naught equals 400 radian per second, and initial phi naught equals pi/6 are considered for the simulation. The results demonstrate that the ambiguous filter we can estimate the unknown input force correctly. Figure 3 depicts the comparison of estimated and true displacement values at a few representative masses, which demonstrate that using the ambiguous filter we can estimate the displacements correctly. We present a second experiment for the problem of estimating an unknown force without any priors using with direct fit-through formulation. We compare our proposed ENAKF filter to other state-of-the-art filters, including ZDF, AKF, and DKF. The results show that the ENAKF filter had the same performance as other state-of-the-art filters in estimating the unknown input force. Figure 5 depicts the displacement estimation of ZDF, AKF, DKF, and ENAKF versus true values of a set of representative masses. We can see that the ENAKF filter is not as good as other filters at estimating displacements. which is because the ENIK filter is a suboptimal filter and its performance depends on the number of ensembles is used. We can increase the number of ensembles to achieve a better estimation result with trading off for computational costs. Table 1 and 2 provide a performance summary amongst the investigated filters. Although the ENIK filter do not perform well in estimation of the displacements, its performance in estimating the unknown and unmodeled input force is comparable to other filters and is the fastest filter when the number of DOF is large. We also see that the MVC filters is the best performing filter across all measure metrics. Hence, if unknown input force is differentiable and can be modeled in advance, the MVG filter provides an optimal method of estimating the input force. In conclusion, we have proposed two novel approaches for estimating an unknown input force applied to a large structural system. If the input force had a sinusoidal form, the MVG filter coupled with a force extraction technique can be estimated force derivative can be implemented to estimate the unknown force in real-time environments for the large structural system. Input force is completely unknown. Our proposed ENIK filter can significantly reduce computational time compared to other state-of-the-art methods without degrading the estimation performance. In future work, there are two potential directions to extend the current work: estimating the unknown input force without collocated measurements, and second, estimating the unknown input force and system parameters for unknown system. Thank you very much for your attention.